Okay, in section 7.4, we're going to look at some special cases dealing with similarity in right triangles. So when we have a right triangle, we have some specific or unique things we can look at. So theorem 7.3, the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original and to each other. All right, so let's put this into a little bit clearer terms. First of all, we need to pretend that this is perpendicular. It doesn't look it, but it should be. So my drawing's just a little bit off. So if that's perpendicular, so it's the altitude. And if I label my original right triangle, sorry, that should be a right angle up here at the top too. Well, let me get my ink back. Okay, so this is a right angle, and this is an altitude. All right, so we're going to label this A, B, C, D. So the original triangle, triangle CAB, and I started at the right angle, went down the short leg and across the hypotenuse to name it, so I'm going to do the same thing with my others, is similar to each of these smaller triangles, and we're going to call this one therefore DAC. The original triangle CAB is congruent to the other triangle that was formed, triangle DCA, and then the two, DCB, starting here, DCB, and then these two small triangles are also congruent to each other. So DAC is congruent to DCB. So the big triangle is congruent to each of the small triangles, and the small triangles are congruent to each other. So using this same drawing, we're going to work on some proportions. So let me reinvent the drawing here. Okay, and we had this D, that was my right angle, that was my right angle, CAB. So let's say that I want to use the ratio of DB is to DC. So DB is the long leg, is proportional to the short leg, and that's of this left-hand triangle. Now I should be able to get, since they are similar, I should be able to do the same thing with my other triangles. So DC, the long leg of the right-hand triangle, is proportionate to DA. And using the big triangle, the long leg, did I start with the long one? Yep, the big leg, which is BC, forms a ratio with CA. So I can form all three of these ratios being given just the original one to start with, which was this left-hand triangle. The long leg is a ratio with the small leg, went to this triangle here, the long leg to the small leg, and then the biggest triangle, the long leg to the small leg. And those are all therefore form a proportion because they come from corresponding parts of similar triangles. So that's one way to use this theorem. Okay, we're going to take a little sidestep and talk about geometric mean. For any two positive numbers, a and b, the geometric mean of a and b is the positive number x such that a over x equals x over b. So let's try one of these. Write that down. Find the geometric mean of 6 and 15. So if 6 and 15 have a geometric mean, it is the number that would be true of this proportion. 6 times 15 is 90. Take the square root of both sides, and I can simplify to 3 root 10. If you don't remember how to simplify, ask me in class. All right, so now I'm going to take that idea of this geometric mean, finding this wonderful number that fulfills this proportion and makes it true. Let's go back and look at this proportion. DC here is the geometric mean of DB and DA, and we're going to use that for our next corollary. So the corollary, the first corollary, corollary 1 to theorem 7.3. The length of the altitude, let me put my right angles in here so that we're all clear. This is my original right triangle, the big one. This is the altitude, forms two more right triangles. Okay, and if I label this again, A, C, B, D. The first corollary says that the length of the altitude to the hypotenuse of a right triangle, so that's CD. CD is the geometric mean, that means it's going to go in these two positions, of the lengths of the segments of the hypotenuse. So I broke this hypotenuse into two segments, DB and DA. So that's our first corollary. So if I give you a triangle with some numbers for some of these sides and ask you to find the altitude, you should be able to do that by finding the geometric mean. Let's put one more corollary up here. Corollary 2 to theorem 7.3, and again we're going to label this triangle the same, ABC. This is my right angle up here and my right angle down here. I know you can't see that because I'm using white. This says that the altitude to the hypotenuse of a right triangle, again CD, separates the hypotenuse so that the length of each leg of the triangle is a geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Write that all down and then come back. So, each leg of the triangle is a geometric mean. So let's start with CA. CA is a geometric mean of the length of the hypotenuse, AB, and the length of the segment closest to that leg, AD. We have another one here because if I take the other leg, CB, CB is the other leg. It's the geometric mean of the length of the entire hypotenuse, AB, and the segment closest to CB, DB. So I get two geometric means using the altitude and the segments of the legs in proportion to the whole leg. I get one geometric mean using the altitude and the two segments of the hypotenuse. And again, all of these will be used with numeric values to solve triangles and find missing pieces. You will need to have these corollaries in your notes nice and neat so that you can use them on your problems. We'll do a couple problems in class before we get going.